things go to Mars. So what we're figuring out how to do staging. All of our destination systems, we are looking at actually pre and placing them robotically ahead of time. Send them out kind of on the slow boat through electric propulsion, whether it's Mars moons or the surface or an orbit. You pre-place that so you know that your destination systems are working before you send folks. You use this distant retrograde orbit to do your assembly of your transit hab that you want to send back and forth to Mars. You assemble it in a distant retrograde orbit so you don't have to use a lot of propulsion to keep it there. At some point, the crew that's actually going to go all the way to Mars then also rendezvous with it, either in that distant retrograde orbit, or there's some advantages potentially in taking it out of that orbit and actually meeting up in what they call a high elliptical orbit around Earth. And we meet up and then we're on our way to go to Mars. But again, just keeping it as the place to stay. Then the crew would actually transit in less than 6 to 9 months. And we're even looking at hybrid structures, hybrid engines and stuff. Right now, that's with a traditional chemical engine. We also have investments in nuclear thermal propulsion as well that could shorten it down. And the latest kind of thought is actually combining high-power solar electric propulsion with a chemical stage. And you're actually using electric and chemical at the same time. And that is actually a very efficient combination that would get you closer to that six-month duration, getting you out to Mars. The most important part in my mind, though, is on the way back, you don't throw any of it away. The entire stack coming back from Mars gets parked right back in orbit, in the lunar distant retrograde orbit. And the only thing that comes back is whatever crew capsule it is. The crew could actually, at some point, jump off and come all the way back to Earth. Again, it has to be within that 21 days, because that's all they have in the capsule itself. Or you can actually bring the whole thing back, and then Orion can shuttle between Earth and the Moon. And then you have a habitation system there. You do an outfitting of cargo, maybe even commercial cargo out there, and it's ready for its next trip or its next round trip out to Mars. So it gets along that cycler kind of concept, but not quite. If you looked at Aldrin cyclers and some other things that are out there, there's a value of being able to keep it in place to do the retrofit after. So there's a lot of different technologies that we need to advance, and that's what this chart's talking about, from landing large masses on the surface to the large-scale solar electric propulsion. We still need surface power. Surface power is, at this point, is looking like we're going to need nuclear surface power, nuclear surface reactors. Solar is 3 times the mass to land on Mars as nuclear for the equivalent power production, if you look at the total system mass. And Mars is a pesky, dusty place where you drop 0.2% per day solar array efficiency just from the dust settling. So you have to have some kind of active system to clean it off. Now there's techniques potentially to do that with electrostatic discharge and some other things that could be intriguing as well. But right now we're looking at nuclear surface power. And then kind of generating all of our in-situ resource, generating our propellants and even consumable water and such on the surface of Mars itself. So that's a little bit on the architecture side. And now what I was going to dive in is give you kind of a view of some of our actual real investments in hardware we're building. We split things into kind of 4 categories: habitation, vehicle systems, your landers and space propulsion, the crew itself, make spacesuits for the most part there, and robotic precursors or probes that we want to send out there before we actually send the humans. My group, this is a bunch of text here that explains what these areas are, but we're a group of just shy of 600 people across the country, including here at NASA Ames down the street. We manage everything loosely in the project form, although I hate the word project even. That invokes too much bureaucracy and structure in the NASA community. These are technology and capability development efforts. We measure everybody's progress by technical milestones only. So their only product and only deliverable to me is whatever they agreed to demonstrate in the time that they agreed to demonstrate it. All the other paperwork is ancillary, in my opinion. So we have 72 milestones, and actually my goal is actually just to have 80% completion on them per year. So we have a high rate of, in NASA world, we have a high rate of failure reaching milestones as well. And a lot of it's actually in flight. So we are designing the next generation spacesuit. So what you're looking at here is the backpack portable life support system. We have an engineering unit completely working, first one in 30 years. The spacesuit backpack that you see on the space station today is about 30-some-year-old technology with minor upgrades since it was originally built. That backpack is now in human testing, human-in-the-loop testing as we speak. We're doing the next generation spacesuits as well that are significantly lighter weight. We're on our second design iteration of those. And then we're even testing kind of one-off designs of extremely lightweight spacesuits by taking our ascent-descent suits, if you ever saw the shuttle pumpkin suits, the orange suits, taking the same modular portable life support system, putting it on the back of an ascent-descent suit, and you can do a short duration EVA with it. So it's very modular in design and on different garments and different backpacks. A bunch of other investments. We're the ones funding the work with Bigelow for inflatable module demo on the space station. So this is interesting, and I have a graphic of that I'll show you in a minute. All the next generation life support system, whether it's water recovery, atmospheric, remediation and environmental monitoring, to things like radiation protection. We build all the radiation sensors now for all the vehicles. We organize that into one common group, so we have commonality of radiation sensors across our entire portfolio. And every flight that we fly, whether it be robotic or human, is flying a radiation sensor now. And we're getting that kind of data, including the Mars Curiosity data on transit, and now we're operating every day on the surface of Mars today, to things like our 3D printer that we did with a local company here, Made in Space, and actually printing ABS plastics on board station today. And later this year we'll fly up an actual unit that fits in one of our lockers on board the space station that's more of an additive manufacturing facility that will be permanently up there. This is more of a test. But things like large-scale fire is bad in space, kind of bad everywhere, but in space we don't really understand large-scale flame effects. The largest thing we ever burned in space is the size of a Post-it note, 4 inches by 4 inches. This is going to be a meter by half meter. Really big flames, maybe. We don't actually know. And we're taking it to the space station in one of our commercial cargo vehicles, orbitals. And after, the key thing is after we undock, when it's done, the last thing the astronauts do is they pull our safety pins for all of our pyros. And after we get away from the station, then we'll actually activate our experiment and cause the fire to occur on the inside of the module. And film the whole thing in high definition TV and see what it actually does. We have theories about large scale flame dynamics and all this stuff, but we've actually never done it. And where this matters is because we don't understand it, we don't really understand how to pick the better materials, how to do design. So what we do now is we test the hell out of everything, which costs a lot of money. It'd be better to have some physics to base our models off than just physics by themselves. Sometimes things don't behave the way we model. So look for that. That's actually coming up late this year, well, actually early next year at this point. So getting back to the Bigelow module, so we initiated discussions with Bigelow 2 or 3 years ago at this point. over 10 years ago at this point, they actually licensed exclusively the trans head technology for those that are kind of space followers of things. And they've been advancing the inflatable